Lesson 4.3, Conditional Probability and the Multiplication Rule. Example 1. The table represents the number of U.S. men and women in millions, 25 years old and older, who have attained various levels of education as of March 2007. A. What is the probability that a person chosen at random is a woman who is a high school graduate? Alright, so the first thing we're going to want to do is add up all of the columns in our table, which I have done right here and here. And also we want to add the rows, and I have the totals out here to the side, so our grand total is 195. Okay, so we are looking for the probability that the person is a woman who is a high school graduate. Alright. The women high school graduates are right here, the 31.9. So the probability of a woman and a high school graduate is going to be that 31.9 divided by everybody who's involved in the survey, which is there's 195. And when we put that in the calculator to get our 3 decimal place estimate, we get 0.164. B. What is the probability that a person chosen at random is a high school graduate? Alright, well, all of our high school graduates are right here in the 61.5, and then the total, of course, is over here at 195. So the probability of a high school graduate is going to be the percentage of high school graduates divided by our total here. And when we put it into the calculator to get our 3 decimal estimate, we get 0.315. C. What is the probability that a person chosen at random is a woman, given that the person is a high school graduate? Okay, if we follow the formula, we're looking for the probability of woman given high school grad. Now, according to the formula, we should be looking for the probability of woman and high school grad divided by the probability of a high school grad. Okay? Well, we said the probability of being a woman and a high school grad was right here, the 31.9, divided by the 195, and then the probability of being a high school graduate was down here, it was the 61.5, divided by the 195. Alright, now you have to remember back, in the way back, when you learned how to divide fractions. Remember, you're supposed to do the top fraction there, 31.9 over 195, change this problem into multiplication, and take the bottom fraction and turn it upside down, like so. And then we can see that the 195s are going to cancel out, so we have 31.9 divided by 61.5. And when we get our 3 decimal estimate from the calculator, we get 0.519. Alright, now using the formula is not the only way to do problem C. Because the nice thing about conditional probability is it cuts down your sample space. And so we won't have to deal with all 195 of these people. Alright, we are looking for the probability that a person is a woman given that they're a high school graduate. Okay, that's not going to change. Woman given high school graduate. this second way to work the problem is going to look at only the high school graduates. This is the sample space I want, and so that's going to be all of this stuff right here, and I'm going to ignore the entire rest of the table. So the probability of being a woman in this column is going to be 31.9 divided by the total number in this column, which is 61.5. And I believe that's the fraction that we had after we used the formula a while ago. So when we go into the calculator to get our 3 decimal approximation, we get 0.519 once again. Example 2. In a certain city, 70% of high school students graduate. Of those who graduate, 40% attend college. Find the probability that a randomly selected student will attend college. Alright. Well, we're trying to figure the probability of going to college. Now, according to our formula, the multiplication property, the probability of an event is actually equal to, this is A and B, this is equal to the probability that event A happens times the probability that A happens given that B has already happened. Nope, that's backwards. We want the probability that B happens given that A has already happened. Okay, so event A here is going to be the 70% of high school students who graduate. Okay, and then event B is going to be the ones who attend college. Alright, now, notice the way this is worded. Of those who graduate, 40% will attend college. Another way to say this is that the probability of going to college, if you know they've graduated, is 40%. So the probability of college, given that they did graduate from high school, is 40%. Okay. So if we want to know the probability of college, and I guess it's probability of college and high school, or high school and college graduates, so we can change this. Alright. So this is going to be the probability of graduating from high school times the probability of attending college, given that they've already gone to high school and graduated. Alright, so the probability of graduating high school is 70%, and the probability of going to college, given that you've already gone to high school, graduated high school, is 40%. And so the probability of being a high school graduate and attending college is 0.28. Example 3. 2 dice are rolled. Each comes up with a number between 1 and 6. Let A be the event that the number on the first die is even, and let B be the event that the number on the second die is 6. Explain why A and B are independent. Well, if you're holding the 2 die in your hand and you can roll them one at a time, the first one that you roll can come up any of the sides 1 through 6. And when you roll the second one, nothing is taken away from the probability. There are still 6 sides on that second die. And so the rolling of the first one has no effect whatsoever on the second one. And that is what makes them independent. Okay? Now, for part B, we're trying to figure out the probability of A, the probability of B, and then the probability of A and B. Alright, so the probability of rolling an even number, well, on a die, The sample space is 1, 2, 3, 4, 5, 6. 3 of them are even, and there are 6 in the entire sample space, so this is 0.5. The probability for B, event B, is that the number on the second die is a 6, so we want the probability of rolling a 6. Well, only one of the sides of the die has a 6 on it, so the probability is 1 out of our sample space of 6. Alright, and then when we multiply these two together for the probability of A and B, we're going to have 3 over 6 times 1 over 6. This is 3 over 36. And if we go to the calculator to get the decimal approximation for it to 3 decimal places, we get 0.083. Example 4. A pollster plans to sample 1,500 voters from a city in which there are 1 million voters. Can the sampled voters be treated as independent? Explain. Well, what we need to figure out is what percent the sample size is compared to the entire population. All right. In other words, 1,500 is what percent of 1 million. Alright, so we have 1,500 over 1 million. And if we want to turn that into its percent, we'll multiply it by 100%. And then when we put this in the calculator, we'll get, and this is 0.15%. So yes, we can treat those sample voters as independent because 0.15% is less than 5%, and that was where we had set the standard. Example 5. 500 students attend a college basketball game. 50 of them are chosen at random to receive a free t-shirt. Can the sampled students be treated as independent? Explain. We're going to solve this problem pretty much the same way we did example 4. We need to find out what percent 500 is of, the 50 is of those 500 students. Okay, so we're trying to answer the question. What percent of 500 is 50? Right? So 50 out of 500, and then we turn this into a percent by multiplying by 100%. And this will give us, let's see, 10%. So, can our sample students be treated as independent? No, they can't be treated as independent. And the reason is because our sample size of 50 is 10%. That's more than 5% of the population. So 10% is greater than the 5% of the population. Example 6. An office has 3 smoke detectors. In case of fire, each detector has a probability of 0.9 of detecting it. If a fire occurs, what is the probability that at least one detector detects it? Alright, so the probability of detecting a fire is 0.9. And the probability of not detecting a fire is 0.1. Okay, so these are the probabilities for one fire detector, but we have 3 of them. And so at least one means that maybe the first one detects it, maybe the second one detects it, maybe the first one and the second one detects it, maybe the first, second, and third detect it, maybe just the second and the third detect it, or just the second one by itself. You can see where this is going. So we have way too many probabilities to try and figure out. It could take a while. So what we're going to do instead is we're going to find the probability that none of the fire detectors detect the fire. And then we're going to use the rule of complements, and we're going to subtract that probability from 1, and that will tell us the probability that any combination of the three will in fact detect that fire. Alright, so let's see. The probability that none of them detect fire. Now be careful. This is not 0.1. That's just one fire detector. We have 3 of them. So the probability the first one misses it is 0.1. The probability the second one misses it is also 0.1. And the probability that the third one misses it is also 0.1. And when we multiply these together, we get 0.001. So that's the probability that all 3 miss the fire. Okay? So now the probability of at least 1, which means 1 or more, is going to be 1 minus the probability of none of them detecting. And in this case, that's going to be 1 minus 0.001, and that is 0.999.